Hello everyone, welcome to another episode of Math-321. So today we're going to finish up Investigation 28 and we'll start into Investigation 29. So Investigation 28, this is products of groups. So here are the most important things that we learned last time. So we learned the definition of an external direct product. Let G and H be groups with operations that are denoted like this. This is the multiplication in G and this is multiplication in H. Then the external direct product of G and H is the Cartesian product, G cross H. So those are the elements that make up the external direct product. They're the ordered pairs. Together with an operation defined component-wise, that is, if we multiply two ordered pairs like this, where the first one is from G in each of those and the second one is from H, then we get another ordered pair where we've just done element-wise or component-wise multiplication, multiply the first two ones together in G, and multiply the second two ones together in H. So that's all it is. And then we talked about the internal direct product. So let G be a group with identity E, and let K and N be normal subgroups of G, such that the intersection of K and N is only the identity. Then the internal direct product of K and N is the subgroup, which has this very confusing notation. It is the same notation as a Cartesian product, unfortunately. I'm going to read that one as K times N. So K times N is this set right here. It's all of the elements from K and N just multiplied together. Okay, so let's get into some new material. Okay, so some groups, like U28 for example, can be decomposed into K times N for the right choice of K and N. So if you choose the right normal subgroups, you might be able to write that U28 equals K times N. So for this activity, we're going to let the group G be U28. And if you forgot what that is, this is the operation table down here, and these are the elements that are in U28. And then the normal subgroups are going to be the cyclic subgroup generated by 3 and by 13. So go ahead and try this activity, and then we'll go over the answers. Okay, so let's go ahead and go over the answers here. So we need to determine the elements in K and N, and then figure out what their intersection is. Okay, so K is going to be the cyclic subgroup generated by 3. So first of all, it's going to have 3, and then it's going to have 3 squared. So the operation in U28 is multiplication, so that's why we're doing squares and not integer multiples. So that's going to be 9. Oops. 9. Okay, and then we do 3 cubed, which is 27. And then we do 3 to the 4th, which would be 81, but 81, I think we have to do mod 28 to that. So let me see, where is 9 times 9 in this table? Let's see, 9 times 9. Okay, that's 25, so that'll just save me some time there. Okay, and then we keep going. So we'll do 3 to the 5th, which would be, 243? But instead, I think that's, if I want to use this table here, I can just do it as like 9 times 27, for example. So let's see, 9 is here and 27 is here, so that will be 19. Okay. And then let's keep going because we still haven't gotten the identity yet, which is 1 in this case. So 3 to the 6th, that should be 27 times 27. So let's do that in the table here. So 27 times 27 is 1. Okay, so we got the identity, so that is the end of that cyclic subgroup. Once you get the identity, that's everything. Let me just write it out a little bit shorter here so I can see it a little more easily. So 9, 27, 25, and then what was the next one? 19, and then 1. Okay, and then for N, same way, but just with 13. So first we get 13, and then 13 times 13, or 13 squared. So that's going to be here, here. Oh, that's 1 already, so that one's quite short. Okay, so then what is in the intersection of these two? I think I see there's only one thing in there, right? It's just the identity, 1. So that's exactly what we need to make the internal direct product. We need that the intersection of the two groups is 1. And in this case, these two subgroups K and N, they will be normal because this group is abelian, so the left and right cosets would be the same thing. Okay, so I just copied and pasted this on here just to remind us what K is, and then N is 13 and 1. So we want to find a way to write every element in U28 in the form k times n for little k in big K and little n in big N. And I think this hint actually here is not very helpful, although this was from the book, because that's pretty obvious. Like, of course, they can be written in the form of some x times 1 or x times 13, because those are the two elements of n, and then x has to come from k, right? Like, that's the whole point. We're trying to find k times n. Okay, so let me just like circle what is k in this first left column over here, because that's where the first part of the multiplication is going to come from, or the first part of the product. So there's 25, and then there's 19, and then there is 1. And then the two things that are from n are 1 and 13. So let's just look in the table, like what are the elements that we get when we do this. So we're getting these ones, this one, this one. Now let's just see if we can find all of the group elements in there. Okay, so the circled elements here are of the form Kn for little k in big K and little n in big N. And let's just see, did we get all of them? So is 1 in there? Yeah. Is 3 in there? Yep, I see it. Got a 5. Yep. I see 9. I see 13. Do I see 13? Yeah. And do I see 15 right there? 17 is... Where's 17? Oh, right there. And then 19 is here, and then 23 is here, and 25 is here, and 27 is here. So yep, they're all in there. So that's the whole group. Okay, so let's look at a theorem here. So actually, every finite abelian group can always be decomposed into an internal direct product. We're not going to learn why that exactly is until investigation 31. But a natural question about when you're decomposing a group into an internal direct product k times n is whether the representation of each element as k times n is unique. So we saw on that last slide that we identified each element in the group as some k times n, where little k was in big K and little n was in big N. And we did see that they were unique, like there weren't multiple copies of each group element in that product. So that was interesting. And then there's actually a theorem that tells us exactly that. So Theorem 28.15, let G be a group with identity E, and let K and N be normal subgroups of G, such that their intersection is just the identity. Then we have the following two things. So first of all, there's one about commutivity. So little k times little n equals little n times little k for all of the little k's in big K and all of the little n's in big N. So that's interesting. And then secondly is about the representations being unique. So the representation of an element in k times n in the form kn, where the little k is in the big K and the little n is in the big N, that is unique. So there's not multiple ways to do it. One thing to note here is that even though this seems like a pretty strong commutivity result in the first point there, the kn equals nk, that is not necessarily saying that either k or n are commutative or abelian, nor is the group necessarily abelian. It's only that it's only that elements of k commute with elements of n. Elements of k may not commute with each other at all, and elements of n may not commute with each other either. Just the elements of k commute with the elements of n. So that's kind of interesting. Let's look at the proof. Okay, so here is the proof. So this is supposed to be let, so yay, we found a typo. So let G be a group with identity E, and let K and N be normal subgroups of G such that their intersection is only the identity. So to prove part 1, let little k be in big K and little n be in big N. Then we know the following. So we know that K inverse is in N. That is coming from a theorem that I believe was in the previous investigation, that when you do an element times a normal subgroup times the element's inverse, that'll always be in the normal subgroup. Okay, and then similarly we can do the exact same thing to show that this thing is in K, because we're taking an element in the middle there from the normal subgroup of K, that K inverse that's in K, and then you can just push on either side an element and its inverse from the regular group, and that'll always be in the normal subgroup. Okay, so both of those are going to be in N and in K, respectively. So then what you can do is you can multiply together this thing here. We said that was in N, and little n inverse has to be in N as well, because we said N was in N. So if you multiply two elements together that are from capital N, those still have to be in capital N because it's a subgroup, so it's closed. And similarly, you can do the same thing here. This thing is in K, and this thing here is also in K, and K is a subgroup, so it's closed. Okay, so that, if you look at these closely here, it's actually just two different ways of writing the same thing. Like, these are the same thing. Okay, so that element there, that is in both N and is also in K, so it's in the intersection of K and N. And so since it's in the intersection of K and N, that means we already said their intersection was only the identity, so that element must actually be the identity. Okay, then once you find out that that's the identity, you can just do a little bit of algebraic manipulation, multiply both sides on the right by nk, you get a little cancellation, and then you get that nk equals kn. So that goes quite easily. And then for part 2, let x be an element in k times n, and then let's suppose that x has two different representations in the form kn, so k1 n1 and then k2 n2, and then to show that representations are unique, of course we'll need to show that k1 equals k2 and that m1 equals n2. Okay, so these are coming from the little normal subgroups. Okay, so then what we can do is we can take this equation right here and we can multiply through on the left by k2 inverse and also on the right by n1 inverse. And then what's going to happen is it'll turn into this equation right here. Okay. Now what we can say is that since the first one, this one right here, this must be in K because both of those elements are in K. And this one right here, that must be in N because both of those elements are in N. So since that's an equality, they're both the same element, and one of them's in K and the other one's in N, then they must both be in K and N. So they are in the intersection of K and N, and since they're in the intersection, then they must be the identity, because that's supposed to be the intersection. Okay, so if this equals the identity, and this is another way of writing it that also equals the identity, then you can just do a little more algebra, multiply through by K2, multiply through the other one by N1, and then you get that K1 equals K2, and N1 equals N2. Okay, so that shows that the representation of the element X in K times N is unique. Okay, so that was the end of Investigation 28. So let's move to Investigation 29, Group Isomorphisms and Invariants. This one will be kind of fun, I think. Okay, so here are our focus questions. Intuitively, what does it mean for two groups to be essentially the same? What does it mean for two groups to be isomorphic? How does the definition of isomorphism reflect the informal definition of essentially the same? What strategies can be used to prove that two groups are isomorphic? How are these strategies motivated by the definition of isomorphism? What is an invariant, and how does one prove that a property is an invariant? How can invariants be used to prove that two groups are not isomorphic? Can invariants be used to prove that two groups are isomorphic? What are isomorphism classes, and what is their role in the classification of finite groups? What does Cayley's theorem say, and why is it important? Okay, so basically what we're going to do in this section is about the idea of sameness. So this notion of sameness is very important in mathematics. You know, we talk about equality a lot in mathematics. And in this investigation, we're going to define what it means for two groups to be essentially the same or isomorphic. Okay, so here's a preview activity for us to start off with. So the operation tables for 4 groups are shown below. Which of these groups would you consider to be essentially the same, and which would you consider to be different? Consider each possible pair of groups and give a convincing argument to justify your answer for each. So keep in mind here that you can rename the elements of a group and it will still be the same group. So it doesn't matter that they have differently named elements. That's unimportant. And you can also rearrange the rows and columns of a group without changing the group. So you have the ability to rename elements and rearrange rows and columns and see if you can use those things to show that any of these are the same or that they're not the same. Okay, so let's go over this activity. So this is pretty challenging actually because there's many different ways. You could actually count how many different ways there are to rename, for example, the elements of G1 to have the names of the elements of G2. Like, it's pretty obvious to try replacing A with alpha and B with beta and C with gamma and so on. But there's more ways than just that. And so you would really need to check every single one of those ways to see whether you got the same group or not. And there's also many different ways, well, 8 factorial ways, right, to rearrange the rows and columns of these groups. So it's way too many to check, right? So we have to be a little bit clever about what we're going to do here. Is there something about these groups that is like fundamentally different from each other? So one thing you could check is whether they are abelian or not. So if you want to check for whether a group is abelian, you want to think about doing the transposition of the matrix Is that what it's called? It's been so long since I've done linear algebra. So basically, like, you want to try reflecting over this diagonal line right here and see whether you get the same thing when you reflect across it like that. And if you do, then it's abelian. And if you don't, then it's not abelian. So which of these groups is abelian and which are not abelian? So this first one, G1, it's actually kind of hard to see that it's not abelian. There's only a couple elements where it doesn't work. So I think B times E is H, and E times B is F. So this is not abelian. All right, now if we look at G2, I think you can see pretty clearly that G2 is abelian. So like G1 and G2 cannot be the same because they don't have the same properties, right? Now G3 and G4, I believe those actually are abelian. So that tells us right away that G1 is not the same as any of the rest of them because it's the only one that is not abelian. So now we have to look at comparing G2, G3, and G4. So 3 possible pairs that we could make there. Now, G2 does have this property where, like, you get these diagonals that are all the same, like this. These are all the same, these are all the same, and it is the only one that has that property, but we can't really know for sure that the others don't have that property when we rearrange the rows and columns, so that's not actually like a very good property to try to check, because you could certainly rearrange the rows and columns of G2 and make it lose that property. So that's not like the best thing to check. So let me show you another thing that you can check actually. So if you look along this diagonal right here, so this is all the squares of the elements, and it's pretty easy to identify what the identity is in each of these groups. Like in this one, this is the identity, and in this one, this is also the identity. In fact, I think they've all been written with it just in that first column and row there. So you can see that some of these elements here along this diagonal that I've circled, some of them do give you the identity, and some of them don't, right? So like G2 has 2 elements that are the identity when you square them. So one is the identity, and then one is something else when you square them. So 2 elements that are their own inverse, basically. Okay, so let's look at that, if that is the same in any of these other groups. So along the main diagonal here, there's an S here, there's an S, so that's the only other S. So G3 has the same property as G2 there. But let's see about G4. So G4, the identity is the spade symbol. So we got one there, one there, one there, and one there. Okay, so G4 is different. G4 has 4 elements that are their own inverse. So G4 then is going to be definitely different from G2 and G3. So G4 is not the same as G2, and G4 is not the same as, that's the 6, G3. Okay, so is there anything else we could look at? So we could keep looking at that main diagonal thing. Maybe that would be helpful to distinguish between G2 and G3. So I think along the main diagonal of G2, how many different elements are we seeing there actually? I think I'm seeing 4 different elements. It's alpha, gamma, epsilon, and eta. And then along the main diagonal of G3, if I look along here, how many different elements am I seeing there? 1, 2, 3, 4. I'm also seeing 4 there, so I still can't really distinguish between G2 and G3. So you could keep trying stuff like this, like you could try taking more powers of elements and stuff like that, but it's a lot of work. So I think we'll stop there with this sort of just a question mark on whether G2 and G3 are the same. And we'll actually resolve this later on in the lesson. Okay, so yeah, so to summarize, we found that G1 and G4 are different from the others, and then G2 and... Okay, so let us continue with another activity. So I want you to try substituting the Greek letters alpha, beta, gamma, delta, epsilon, zeta, and eta, and theta for 0, 1, 2, 3, 4, 5, 6, and 7, the congruence classes in Z8. So the table here is the operation table for Z8, and so what you're going to do is whenever you see a 0, you're going to replace it with alpha, and then you're going to replace all the 1s with betas, and just proceed like that in order. And then I want you to see what you notice when you do that. Okay, so let's go over this one. So I'm going to replace all my zeros with alphas, and then 1 with beta, and then this will be gamma, delta, epsilon. No, I think I'll write my epsilon like this. And then zeta, oh, that's a hard one. And then eta and theta. Okay, so if we make all of these replacements, this alpha, alpha, all my betas are my 1s, beta, beta, beta. There's more betas down here, actually. Beta, 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 beta. These are alphas. Okay, and then gammas are for 2s. Gamma, gamma, gamma. Okay, you guys don't need to see me do this whole thing, right? Like, I'll just put etc. So basically what you get is you get exactly this. You get exactly G2. So secretly, G2 was actually Z8, just kind of in like a disguise, you know, we put like a little wig and a hat on all the elements there and disguised them as Greek letters. But other than that, they are exactly the same. Okay, so let's continue on with the kind of the thought process from that last activity. So we saw in the last activity that G2 and Z8 are essentially the same, with the only difference being what you call the elements. So let's try the same technique. Remember, we were wondering if G2 and G3 were the same. Let's try the same technique to see if G3 and Z8 are the same. So let's take the operation table for G3, and let's replace S with 0, T with 1, U with 2, etc., just going in alphabetical order. So when you do that, you actually get this table that is over here on the right. But the problem is this is definitely not Z8 because, for example, 3 plus 1 is not supposed to be 0 in Z8. It's supposed to be 4. Okay, so does this necessarily mean that G3 and Z8 are not the same? Well, no, because we only tried one way of replacing the elements. So there's a lot of different ways that we could replace them. Actually, there's 8 factorial different ways that we could do it, which is way too many to try, unless you have a computer. Even with a computer, it might take a while. So let's think about trying to do this a little more strategically. Okay, so here is a clue to our strategic, the ways that we should try replacing these 0 through 7 elements with the S through Z elements from G3. So in G3, if you take the operation table out and you look at the element W, we already remarked that the identity was S, so that would be like W to the 0. And then, of course, W to the 1 is just W. And then if you look at the other powers of W, W squared gives you T, W cubed gives you X, W4 gives you U, W to the 5th gives you Y, W to the 6th is Z, and W to the 7th is Z, and then W to the 8th is S again. Same as the identity. So what this tells us is that W is actually an element of order 8. Right, so you run through all the powers, and then when you get to 8, you're at the identity, so that's the whole cyclic subgroup generated by W. So W is an element of order 8. So if we're going to make a replacement of the elements from G3 with the elements from Z8, what we need to do is make sure that we replace W with an element of order 8 from Z8. So there are more than one element in Z8 with order 8. There's also 3, 5, and 7. I believe all the ones that are relatively prime to the modulus. But anyway, we need to pick one of those to replace W, otherwise it's definitely not going to work. Okay, so what we're going to try now is we're going to try replacing W with 1, which is of order 8. And then we're going to replace W squared, which was T, with 2. And then we'll replace W cubed, which was X, with 3. And then W4, which was U, with 4. And you see what's going on here is like I'm taking the superscript, not the superscript, the power there, and I'm using that to make the replacement. Okay, so like the squared one is being replaced with 2. Okay, so this is a little more strategic way of doing it. And when you do that, you get this table over here. And this actually is Z8. So it doesn't quite look like Z8, because the elements are arranged in a weird order. Like usually you would have 1 coming before 2, and then 3 would come like before 4. But other than being in a weird order, it is Z8. The operation is done the same way as it is in Z8. So what we can say from this is that G3 and Z8 are essentially the same group. And also, like we were wondering about before, G2, because that was essentially the same as Z8, is also going to be essentially the same as G3. Okay? Because we found they're both the same as Z8. Okay. All right, so this brings us to the informal definition of what it means for 2 groups to be essentially the same. So informal definition 29.3, let G and H be finite groups. The group G is said to be essentially the same as H if the operation table for G can be transformed into the operation table for H by doing nothing more than renaming the elements of G and/or reordering the rows and columns of G's operation table. Okay. So this is our informal definition, and we'll dispense with it once we get to a formal definition. But this is the way you want to think about this concept. So if you want to show that 2 groups are essentially the same, then you need to find a way of renaming the elements of one so that the operation tables become identical. You might also have to rearrange the operation tables rows and columns. But on the other hand, if you want to find that 2 groups are different, that can actually be a lot easier, and that's exactly what we saw in that preview activity. It wasn't too hard to show that 2 of the groups were different, but we couldn't really think of a way to show that 2 of them were the same. So for example, if we can show that one group is abelian and the other is not, then they're definitely not the same group. If one has an order 8 element but the other does not, then they're not the same group. So one thing we could notice, going back to the preview activity, remember we said that G1 was not abelian because EB was not the same as BE. G4 was abelian though because its operation table was symmetric. So that meant that G1 and G4 could not have been the same group. So that brings us to a next activity. Okay, so activity 29.4, they want you to find some further differences between G1 and G4 other than just the abelian thing. So go ahead and pause the video and try this, and then we'll go over it. Okay, so let's talk about this. So another difference that I noticed between these 2 groups is the same one that I was telling you guys about before when you look at the main diagonal here. So in this one, the identity element is A, and we see that A appears 6 times in there. So there are 6 elements that are their own inverse. And then over here in this one, the identity element is the spade, and spade appears 4 times in there. So we can write that as one of the differences. So G1 has 6 elements that are their own inverse, and G4 has 4. Okay, you could keep going like that, like taking more powers and stuff. But another thing I noticed just like visually without trying to do any actual math is the following. Like you can kind of split these operation tables into sections where like this part right here only contains A, B, C, and D. This only contains the other 4 elements. This only contains the other 4 elements. And then this part here only contains A, B, C, and D. And this one over here is actually the same. So that only contains the playing card symbols, and then these are the playing card symbols. And then these are the other 4 symbols, and these are the other 4 symbols. So they actually have that in common. But if you look very closely at, let me see, like just the regions that are circled right there, like the ABCD region and the playing card regions, for G1, the operation tables there are not identical because like this is the same ABCD and ABCD, but this is not the same. This is BCDA and this is DABC. Then I think this row is the same CDAB, and these last 2 rows are not the same. Okay. So even if you actually rearrange the rows and the columns there, if you did that, you would be messing up the fact that the ABCD part matches to make one of the other parts match. So there's actually no way that you could rearrange the rows and columns to make those match. But over here, these 2 sections, they are identical, and so that is another difference between G1 and G4. I'm not sure what that difference would mean in terms of like actually multiplying elements together, but it's just something I noticed visually. So I'll write that down. So G1 has the upper left quarter and lower right quarter table are not identical and cannot be rearranged to be identical. Whereas for G4, they are identical. Okay. All right, so now let's talk about taking that informal definition that we developed and making it more formal. So the informal definition, it is a helpful and intuitive way of thinking about what it means for two groups to be essentially the same, but it is also kind of limited because it only deals with finite groups, and it also cannot be used to easily check. If the groups are large, it's really hard to actually check all the different rearrangements and all the different renamings that you could do. So we really need a more formal definition that we can actually do some math with. So let's think about how we can formalize the important parts of that informal definition. So a way to formalize the renaming of elements is to use a bijective function. So for example, we can rename the elements of Z8 with the element names from G2, which are those Greek letters, using a function phi that maps from Z8 to G2 in the following manner. So phi of 0 is alpha, phi of 1 is beta, phi of 2 is gamma, phi of 3 is delta, so on and so forth, just in alphabetical order. So that's actually what we were doing on that previous activity where we were renaming the elements of Z8 to be the Greek letters. We were applying this function, basically. Okay, so note here that any function that corresponds to a valid renaming would have to be a bijection. And that's because it wouldn't make sense for two elements to be renamed the same thing, so it would have to be injective. And it also wouldn't make sense to leave out any group element and not cover it, so it would have to be surjective. Okay, so the other thing we need to formalize to get our proper definition of groups being essentially the same is that we need to make sure that the two group operation tables will be the same after the renaming. So in other words, that means that the operation needs to work the same way both before and after the renaming. So to say this more specifically in an equation form, for any elements A and B that we're renaming, we need that phi of AB equals phi of A times phi of B. So this is saying that, let me kind of try to put this into English. So this is saying that applying the renaming, maybe I could say it like this, doing the renaming, that's after multiplying. So the one that I have pointing there. And this is doing the multiplying after the renaming. So we need that we get the same result whether we multiply first and rename after, or whether we rename first and multiply after. That's to make sure that the two group tables will actually be exactly the same. Okay, so let's move forward with this definition. All right, so here we've written up the definition as 29.5. Let G and H be groups. An isomorphism is a bijective function phi from G to H, such that for all x and y in G, phi of xy is equal to phi of x times phi of y. And if there is an isomorphism from the group G to the group H, we say that G is isomorphic to H, and it's denoted like this. You might have seen this notation before. It tends to get reused in a lot of different places in math to mean some type of equivalence. So a few notes here to make clear is that, first of all, the isomorphism relationship is symmetric. So if phi from G to H is an isomorphism, then phi inverse from H to G will also be an isomorphism. Furthermore, if you write the group operations additively, then you're just going to replace the products with sums like this. So the equation would then be phi of x plus y equals phi of x plus phi of y. So you need that for additive groups. And then it is also possible for an additive group to be isomorphic to a multiplicative group. So these last two here are covering those cases. If G's operation is written multiplicatively and H's is written additively, then your condition looks like this. because x and y are going to be from G, so they'll be doing multiplication, and then phi of x and phi of y, those are elements from H, so those ones you would add together. And then you can do it the other way around as well. If G is the one where you're adding, then these are the G elements, so you'll add them, and then if H is the one where you're multiplying, then these two are H elements, so you're going to multiply those. So just do the group operation that goes with each group is the main thing. A little note here about the word isomorphic. So this comes from the Greek. Iso means equal. You might encounter that in other places in math, things that start with iso. It means equal or the same. And then morph means shape. So this is like saying that the two groups have the same shape, the same structure, basically. Okay, so let's do a little activity here. Go ahead and pause the video and give this a try, and then we'll go over it. Okay, so let's go over part A. Use definition 29.5 to explain why the function phi from G3 to Z8 from preview activity 29.1, defined by phi of w to the k equals k, is an isomorphism. So here I just wrote out the powers of w again, just to remind you of what they actually are. So this is going to be a bijection, so let's argue why it's a bijection. So phi is a bijection because, well, I think you can see here that the powers of w actually do run through all of the elements of the group G3. So this is going to put the elements of the group G3 into a one-to-one correspondence. You're going to match up one from each between the two groups. So it's matching each element from G3 with one from Z8. So it's injective, and it's surjective because w to the I, or w to any power, runs through all the elements of G3. Hope that makes sense, that argument. You could maybe argue a little differently probably if you wanted to. Okay, so then that's not the only thing we need for this to be an isomorphism. So we need to check the following. So we need to check that if we do the operation before or after the function, that we get the same result. So in other words, that phi of w to the I times w to the j is equal to, okay, so over here on the right side, I'm going to write it with addition, because addition is the group operation for Z8, and on the right side of this equation, I have two elements from Z8. Okay, so this right here, this is the G3 operation. And then over here, this is the Z8 operation. Does that make sense? I hope. And that's for all I and j. Okay, so yeah, let's just check that. So using the way that the phi has been defined, we can say that the left-hand side here is phi of wi times wj, so we can add those exponents together, I plus j. So where is this going to get mapped to by the phi function? That is going to be this, I plus j, like that. Okay, and then the right-hand side is, so this will be a little bit easier, so phi of wi plus phi of wj is just going to be I plus j. Okay, so these are actually the same because in Z8 we're allowed to actually just add those together inside the brackets like that. Okay, so these are the same. So phi is an isomorphism. Okay. All right, so let's look at part B here. So is G2 isomorphic to G3? Use definition 29.5 to justify your answer. Okay. Okay, so we just showed that G3 is isomorphic to Z8. So if we want to show that G2 is also isomorphic to G3, what we can do is show that G2 is isomorphic to Z8, and then that will take care of it. So that's what I'm going to do. I'm going to say G2 is isomorphic, it's not how you spell it, to Z8, because if we rename, what is the renaming we do? Okay, we rename 0 to alpha, 1 to beta, 2 to gamma, and etc. through just in alphabetical order. Then we get the Z8 table. Okay, or rather we get the, I guess we get the G2 table if we're doing the renaming in that order. Okay, so G2 is isomorphic to Z8, and G3 is also isomorphic to Z8 from part A, and then that means that G2 and G3 should also be isomorphic to each other. Okay. Alright, so part C, use definition 29.5 to explain why the function phi from G2 to G4, defined by these parts here below, is not an isomorphism. Okay, so what we can say about part C is that this function, pretty clearly this phi function, does look like a bijection to me. So that means we're going to need to find the following. So we need to find elements in G2 such that the other part of the definition doesn't work, so that phi of xy does not equal phi of x times phi of y. So let's just see if we can pick some random ones and see if they work or not. I think I'll focus on maybe a part where the table actually looks pretty different, like it starts to be different right around here maybe, which would be this. Okay, so I'm going to try doing x equals, let's see, what is the element there? Heart? Oh no, I'm supposed to be picking elements from the first set, right? So x and y are going to be beta, and then that doesn't look like a beta, and then y can be delta. Okay, then phi of xy is going to be phi of beta delta. Still doesn't look like a beta. And so what is beta times delta? That is epsilon, which in case it's going to be phi of epsilon, and then phi of epsilon is just moving it down here. That's called the oh god, I looked this up last night. It's the Pate cross, I think. Pate cross or Patty cross. It's like a medieval symbol. Okay, so that is that. And then what about, can we compare that to phi of x times phi of y? So that's going to be phi of beta times phi of delta. So what is phi of beta? That's going to be the heart. And then phi of delta is going to be the club. Okay, so if we do that operation in the table over here, heart times club, we actually get spade. That's the one that I circled there. Okay, that doesn't, Let me just do, oh, my eraser not gonna erase, oh no. Okay, so unbeknownst to you guys in the background, some PowerPoint errors just happened, and now I have to live with this wonky spade for the rest of my life. Maybe I can just try, oh, is this better? Okay, let me just color it in a little, okay. All right, that's my spade. So in any case, the pate cross is not the same as the spade, so these are different. So this is definitely not isomorphic, or not an isomorphism. Okay, so part D here, what does this allow us to conclude? Well, what does it allow us to conclude? I mean, we found that phi is not an isomorphism, but does that necessarily mean that there is no isomorphism? We only checked one possibility. So part C only checked one possible isomorphism. so it doesn't really allow us to conclude anything. So there's certainly a lot more different ways that we could try putting a bijection between the elements of G2 and G4, and this was just one way. So yeah, there's no real conclusion here, just that this particular way didn't work. So next time we'll talk more about how you can prove that two things are not isomorphic. So that's it for today, guys. I'm going to stop it there, and we will resume Investigation 29 next time.